afternoon, friends. Welcome to this third talk on spar gears. This is under the banner of QEEE program. So in the first two talks, we had quite a elaborate discussion about why we need gears. We introduced to you the topic of gears. We also introduced the different geometrical terms and terminologies associated with the gear. Then we took a deeper dive and we understood the requirement of fundamental law of gearing, and the requirement of fundamental law of gearing is by no means a trivial condition. It can be satisfied only through specific tooth profiles, and it so happens that involute gear tooth profile is one such tooth profile, which is called a conjugate tooth profile. So when we have involute tooth profiles on gears, fundamental law of gearing is assured, which anyway means that the constant velocity ratio is assured. And with that, we have been dwelling on these aspects of involutometry, and we had understood the concepts like pressure angle. We ended the last talk with a topic with that introduction and discussion around interference and undercutting. So we'll take it off from there before we go to gear trends. So I'll straight away go to the topic of interference, which is where we left in the last lecture, and we understood that there is a formula that is available which can be derived easily from again basic geometrical considerations using laws of trigonometry. We derived this formula which enables us to sort of guarantee that if the number of tooth in the pinion is greater than what is shown in this formula, then the interference will not occur. So interference can be avoided in spar gears, the easy condition being given in this form. And undercutting is a special form of interference which happens between a rack and a pinion, and this is with parlance to gear manufacturing process using rack cutter. So when that happens, the formula that was shown in the previous slide can be specialized to the following form, which is given here, and for phi equals to 20 degree, this comes around 18 tooth. So minimum number of tooth that is required in order to prevent any undercutting is 18. If you have a gear tooth, if you have a gear with a number of tooth less than 18, then that gear tooth is susceptible to undercutting during its manufacturing operations if it were to be done using a rack cutter. Okay, now we come to another important concept, that of contact ratio. So in the last class it was explained that the contact between the two teeth will happen along the line of action. So this internal tangent to the two base circles is going to carry the point of contact. So the contact is to happen wherever the line of contact intersects the two addendum circle. So please recall, in our last discussion we had this discussion that the start of engagement is where the common normal is going to common normal is at the point of contact turns out to be the common tangent between the two base circles, and the start of engagement between a gear tooth pair will happen when there is an intersection of the addendum of the driven as shown in this red circle with this internal tangent. Then the engagement will start, and similarly engagement will stop when the driver addendum circle intersects with this common internal tangent. So we'll return back to this picture now as we study contact ratio. I'll come to the concept of contact ratio in a minute, but before that let me explain to you this picture. So what we have shown here is that there are two gears, and as usual we are always showing only one tooth pair in contact. So here the engagement starts from this position, which is where my mouse is scrolling. So here you see that the addendum circle is just intersecting the line of action. So the line of action is this common tangent AB. The two circles that you see drawn in dotted lines are the base circles of the two gears. So AB is the internal tangent to the two base circles. Line of action, which is AB, which is just the internal tangent to the two base circles, and the engagement starts where the addendum circle of the driven gear first intersects this line of action. So that happens to be this point where I am holding my mouse cursor. Similarly, the engagement ends where the addendum circle of the other gear, which is the one shown in red, is intersecting this line of action. That happens at this point. So the point E to F, or the segment E to F, is where exactly the engagement occurs. The engagement occurs in this line segment EF. So what we decide to do here is that we will try to find out an expression for EF. And as the name suggests, in our study of contact ratio, what we are trying to determine basically is we are trying to determine a condition to ensure that always at least one tooth pair is in contact. So before the disengagement happens between this tooth pair, that is by the time this blue tooth has moved to this position, which is indicated by T, another tooth, the one which is following the tooth which is shown in this diagram, that tooth will take the position and it will start engaging. So we are trying to determine that condition, and that condition leads us to the concept of contact ratio. But as I said, let us do it step by step. First we will determine this length of this line segment EF wherein the contact is happening. So here we see firstly that by property of involute, BE is equals to BS. Let me illustrate to you in the notes here. So if you recall, the definition of the involute suggests that a string has to be unwound, and as the string is unwound, any point, for example the point at the tip, will form a involute, right? So the in the position that is shown here, the tracer point, which is this point, as the string is unwounding, this free end of the string is tracing out the circle as has been shown by these dotted lines. Now the question is that whether this length, which as is indicated in this diagram, or let's call this A, B and C. So the in the position that has been shown, the amount of string which has been unwound, the length of the string which has been unwound is BC, right? But in the wound condition, when the string was wounded up, this same amount of string would have occupied the position of the circumference on the circle as BA. So on unwinding, BA portion of the string will be unwound to BC. Therefore, the length of BA has got to be equal to the length of BC. So using this argument, what if we now return to the picture that we were looking at, so the BE portion of the string which has basically got unwound, if it were to be in a wound position, it would have a portion of the circumference BS. So BS portion of the string when it is wound up on the circle will conform to BE portion of the string when it is unwound. So as a result, BE has got to be equal to BS. Similarly, BF portion of the unwound string has got to be equal to BT portion of the wound string. So BT is the part which is lying on the circumference. I could not write the T exactly here because it was looking too cluttered, but the point T corresponds to the point on the circumference of the base circle. Just like the point S corresponds to the point on the base circle, it is not at the addendum circle, it is at the point of the base circle. So we have BE equals to BS and BF is equals to BT as per this argument, which means BE minus BF, which is basically EF. BE minus BF, the left hand side, is equals to EF. That will be equals to BS minus BT. BS is this portion and BT is the smaller arc. So BS minus BT is ST. So therefore our first result is EF is equals to ST from this argument. Also we note that EF can be alternatively written as EF plus AE, EF plus BF, but then when we are double counting EF, so we will subtract one EF, we will also subtract AE, we will also subtract one BF. So therefore EF could, just a simple algebraic manipulation, could be written in this form: EF plus AE, EF plus BF minus of AE minus of BF minus of EF. Right? So this is what we have. Now EF plus AE, EF is this and AE is this, is obviously AF. Right? Similarly EF plus BF is BE, and this last bracketed term AE plus EF plus BF altogether is AB. So EF, which is the length of the contact, is going to be AF plus BE minus AB, and we will determine each of these ratios. So if we look carefully, AF, again we are redrawing this figure here, but this time we are doing only the triangles, right? So what we need to find is AF. We note that AB is a tangent, so that means O1A is a perpendicular to this tangent, O1A being the radius vector of the base circle. So therefore the radius and the tangent will form a 90-degree angle, and therefore if we take a triangle which is O1AF, then it is a right angle triangle, and we may determine the side AF of this right angle triangle using Pythagoras theorem, which states that it is going to be equal to square root of RO1 square. This is O1 because this is the addendum circle. So O1F is basically the addendum circle radius of this gear. I call it gear 1. Okay. So addendum circle radius of gear 1 is denoted as RO1. The base circle is RB1. So base circle happens to coincide with O1A. Therefore AB is going to be square root RO1 square minus RB1 square, which is what I have written here. Similarly, you can calculate BE. So BE, which is here, can be calculated by considering this right angle triangle, which is O2BE. Again, O2B is the radius of the base circle of gear 2, and AB being tangential to the base circle of gear 2, the radius vector and this line AB will form a 90-degree angle, and therefore the triangle O2EB is going to be a right angle triangle. Now O2E is basically the addendum circle radius of gear 2. O2E will be the addendum circle radius of gear 2, and O2B will be the base circle radius of gear 2. So therefore we will have BE, which is this line segment, is going to be hypotenuse square minus base square, which is square root RO2 square minus RBT square. So these are the two formulas for AF and BE. AB is much easier. AB can be determined as AP plus PB, right? And AP is RP1 of sine multiplied by sine alpha. Alpha is the pressure angle which we denoted in the earlier talk by phi. Here in this nomenclature it has been shifted to alpha. So alpha and phi basically mean the same thing in this talk. Both denote the pressure angle. Pressure angle is the angle between the radius vector of the base circle and the radius of the radius vector of the corresponding to the pitch circle. So in this position you have this to be alpha, and anyway it was shown that the base circle is cosine of the pitch circle radius. What we are interested at this point is the length of the line segment AP. The length of the line segment AP is going to be RP1 sine alpha. Similarly, the length of the line segment PB is going to be RP2 sine alpha. So as a result, AB will be RP, AB will be AP plus PB, and that eventually becomes RP1 sin alpha plus RP2 sin alpha. We can take the sin alpha common. Alpha is anyway given as the pressure angle phi. So interchanging alpha and phi, we have this to be the formula for AB. So therefore, the length of action EF can now be determined, and the length of action we know EF is equals to ST. So this EF is equals to ST, that we have already gone through. So what we have at this stage is that the length of the action has been determined. Now what we want is, what is the distance between the two teeth on the base circle. We remember the definition of circular pitch. The circular pitch was distance between the two circles on the pitch circle radius. Here we will reference, this is one geometrical terminology which will be referenced not with respect to the pitch circle but with reference to the base circle. So in a similar fashion, as we have defined, or as we have derived rather, the circular pitch definition, similarly we can arrive at a base pitch, that is the distance between the two teeth on the base circle instead of a pitch circle. So in the just like we got the expression for the circular pitch as 2 pi rp divided by n, similarly base pitch is 2 pi rb divided by n. So for gear 2, this base pitch is going to be 2 pi rb2 by n2. Now what we must ensure is that this base pitch must be less than the length of action, which basically means before this tooth of gear 2 proceeds into this position, that is position T, the succeeding teeth of gear 2, which is not shown here, actually comes and takes this position of S. If that happens, then before the disengagement of this tooth pair, another tooth pair will come into engagement. So this is a crucial condition which we must ensure, because if it so happens that the base pitch is larger than this length of action, it will simply mean that before the disengagement happens, there is no other tooth pair which has taken over the contact, and as a result there will be an interim period where there is no tooth pair in contact. The following tooth pair which will will come into engagement at some duration of time later. So there is an interim duration where there is no engagement that is happening between the two gear tooth pairs, and as a result the concept of positive drive is lost within this interim time period. That is definitely not advisable, because in that interim time period the mechanism will be moving only because of its inertia. It is not going to move because of one link pushing the other. So this is something that we have to carefully consider while using gears, that is the contact ratio, or this condition, base pitch has got to be less than length of action, otherwise the tooth will not come into contact before the disengagement, right. So therefore we define this ratio as the length as the contact ratio, technically termed as length of action divided by base pitch. Length of action is EF, which is the sum of all these three terms that we have found out, and base pitch is 2 pi rb2 n2. So if we simply put this formula that we have deciphered, so EF is AF plus BE minus AB. AF has been determined, BE has been determined, AB has been determined. So we'll just put all these three in the numerator, and the denominator is simply base pitch 2 pi rb by n. I mean, whether you take it on gear 1 or gear 2 doesn't matter, because this ratio rb by n is going to be the same for both the gears. So this ratio will tell us whether or not the engagement happens continuously, whether or not at least one tooth of pair is in contact at all time instants. So definitely it should not fall below 1, that is the length of action should be more than the base pitch, or in other words base pitch should be smaller than the length of action, such that succeeding gear tooth is not far away and it can quickly come and take the position of the tooth ahead, and thereby ensure that the engagement of the following gear tooth happens before the disengagement of the gear tooth which is lying ahead of it. So therefore the contact ratio definitely should not fall below 1. The one which is advised from empirical and knowledge and also from experience is going to be about 1.3 to 1.4, right? It is usually recommended that we have this sort of a gear ratio, contact ratio, but there are certain high contact ratio gears also which are possible, but for the usual applications we would recommend this sort of a value of 1.3 to 1.4. Please understand, contact ratio is going to be a non-integer number. It is not possible that always one pair of teeth is in contact or always two pair of teeth are in contact. At certain durations you will have one pair of teeth in contact, for certain durations you will have two pair of teeth in contact. So that's why over the in an average sense, if you look at it, it is not possible to have an integer contact ratio. The contact ratio has got to be a number of this sort, which is a non-integer value. Okay, so now with that we will come to the next topic of gear trains. So till now we have been looking at just one gear pair. Now as the name suggests, gear trains is a collection of gear pairs. That is, it is not just one gear pair but number of them. You will require gear trains as opposed to a single gear pair if you wish to achieve a transmission through larger distance, for example, or if you wish to achieve a large gear ratio. If you wish to achieve a large gear ratio, instead of doing it in one stage, you could do it in two stages or multiple stages. In that way, you can save on the space that is required. Instead, if you want a large gear ratio to be attained by a single stage gear, then you will require one of the gears to be very big. That may increase your production cost for one thing, but more importantly, it will add to the space constraints. It will add to the packaging constraints in your vehicle. So therefore, it is possibly better to do it in multiple stages, which is what a gear train will accomplish for us. So we'll take up different types of gear trains in this discussion now. So we will understand that gear trains are required to transmit motion through larger distances, uh, and the reason why a gear train is used as opposed to single large gear, if the distance is smaller, that is, if the distance is smaller, you may think that a large gear ratio can be attained by using a large gear with a small gear. That will not be a good idea, because larger gear will mean larger load, because the gear is a massy object, and to make it to impart a motion to it requires a certain energy. So that is like an energy loss mechanism if you look at it from the transmission efficiency point of view. So it is not a good idea to use a larger gear, because a larger gear will induce energy losses. Smaller gears have less losses. So therefore, it is better to use uh, more number of smaller gears and attain the desired gear ratio, rather than use a large gear ratio, a large gear and attain the gear ratio in a single stage, right? Because in this approach of using a gear train, the energy losses will be minimized. So large number of gears forming a large gear train will also induce energy losses. So one has to take care that you should not use too many number of gears also, because if you use too many number of gears, then again the load on your transmission is increasing, and you would do well to keep it under control, because that is like a parasitic energy loss that is there in your transmission. So one should not try to take an approach where you try to transmit this mechanical power over large distances using a gear drive. That is not advisable. There are better uh, procedures available. For example, chain and sprocket could be a better idea to transmit motion over a large distances. And similarly, if you really wish to do a more efficient transmission for large gear ratio, then it is not advisable to use large number of gears. Use smaller number of gears in a more compact mechanism, and that will be having minimal overheads in terms of energy losses. Okay, so a gearbox, if you look our usual automotive gearbox, this will have multiple gear train arrangement to enable a range of torque speed characteristics. As was talked in the introductory lecture, that in our automotive application we need various torque speed characteristics. Keeping the engine in the same efficient point, we would like to derive or extract all these torque speed characteristics. So therefore, there has to be a multiple gears basically for our diverse driving conditions that we will encounter. So this can be attained not by a single gear arrangement, by multiple gear arrangement. And all that multiple gear arrangement can be very efficiently accommodated in what is known as compound gear train, which is what we will study. Okay, but before we go to compound gear train, let us look at a simple gear train. So in a simple gear train, what we have, the reason we call it simple is because every shaft has only one gear connected to it. And as we know that if one of the gears is making clockwise rotation, the other one will make counterclockwise rotation. And because each of these gears have to be engaging perfectly, we also have the requirement that module of all the gears must be same. That is something again which we proved in the first class, that if two gears have to engage, their modules have to be the same. So therefore the module of this and this have to be same, and similarly the module of this and this have to be same, which means that all the modules of the gears in the gear train have got to be identical. So the analysis for such a gear train, it is simple, as I said, that the velocity ratios can be easily determined from the formula omega 1 r1 equals to omega 2 r2 is equals to omega 3 r3. You will note that I have included a sign here which I was not doing in the earlier cases. When we were analyzing just two gears, we were actually keeping track of the fact that the gears are going to be rotating in opposite sense. If one gear, for external gearing at least, if one gear rotates in a clockwise fashion, the other gear will rotate in a counterclockwise fashion. So that was what we were keeping track manually. But now we will make a subtle change in this formula, which is in terms of this sign, and the sign change will enforce this condition that the sign of the angular velocity will tell us the sense of rotation. So if we take clockwise to be positive, then, and if we get a velocity which is angular velocity which is coming out negative, there's nothing to be scared about. It simply means that the angular velocity has magnitude which is as given by our formula, but the sense of the angular velocity is in the opposite sense, which means it is counterclockwise. So whichever convention you choose, it's just that the flipping of the sense of rotation which matters. So with this little change, you can easily analyze simple gear trains. And even if you can have an internal gear train also, wherein there is an internal gearing. I think I did not talk about internal gearing, so I will just quickly talk about that. So gears in this fashion, which are internally meshing, okay, then you will see that both of them have to rotate in the same direction, right? So internal gears are also pretty common. So both of these gears will have the same sense of rotation, and therefore the sign flipping doesn't occur in case of internal gearing. The law of gearing remains the same, that is, if this is capital R and if this is capital omega and this is small omega and this is small r, you still have omega r is equals to capital omega r. Right. So internal gearing will be very common in planetary gear systems, which is what we will talk. So internal gearing, when we analyze, we will take the same formula, except that we will not care for the sign change, because the sign both the gears in an internal gearing arrangement will have the same sense of angular velocity. Okay. So just a few more things before we leave simple gear train. So if we work out a simple gear train, so let's say we have a simple gear train of this kind. I am showing the side view of the gear train. This is how it looks like. All are externally geared. So what we have is omega 1 r1 is equals to minus omega 2 r2 is equals to omega 3 r3, because there is a sign change. So let's say this is the input and that is the output. Okay. So what we see is that the input output ratio omega 1 by omega 3 is r3 by r1, right? So it actually does not depend upon r2. What the second gear is actually doing for us is that maintaining the same gear ratio, it is actually enabling the mechanical transmission to happen at a larger distance. Suppose we want the power to come out at a further of distance. For example, if you have seen commercial vehicles, in commercial vehicles one really has to transmit the power from the engine to the rear axle. That's pretty large distance. Actually in a rear axle the transmission is taking the power is transmitted through the universal shaft, but this is one case where we can quickly think of a situation where the mechanical power needs to be transmitted over a larger distance. So simple gear trains are used for such purposes. Simple gear train has got no role to play in terms of the gear ratio. The gear ratios are only determined by the sizes of the input and the output gear. The intermediate gears have got no role to play in determining the input output ratio. The input output ratio is completely determined by the input and output gears. The intermediate gears simply play the role of transmitting the motion over a larger distance if that is what is required. And also another important feature which is very handy again in cars is that it reverses the direction of motion. Had I not used an intermediate gear and had I simply connected R1 and R3, I would have got the same gear ratio. In this arrangement, omega 1 R1 is equals to minus omega 3 R3, right? So this is R1 and this is R3. This is R1, this is R2 and this is R3, right? So in this arrangement I would have got the same gear ratio in terms of its magnitude, but the sense of rotation of this gear is opposite. So what the intermediate gear R2 has done is that it has also reversed the sense of rotation. If for some reason I wish to have the output motion in the opposite direction, then I will require an intermediate gear which is actually called the idler gear. And this is exactly what happens in the case of our automotive transmission also. During reversing, all that you require is you require an intermediate gear in between the two gears that were operating in the forward motion, and when you have this intermediate gear you will see that the motion, the direction of motion is reversed, which is very important when you are reversing the car. Otherwise there is no way that you can reverse the car. So that is an important aspect of a simple gear train. So for these two purposes, simple gear train are have predominant application. One is that it enables you to transmit motion over larger distances, and the other is that it enables you to achieve a reverse motion if that is what is required. It is actually not very useful in terms of achieving a higher gear ratio in lower space or anything like that. For that we are going to a compound gear train. So the reason why we refer to this gear train as a compound gear train is the following. Here as you see in this diagram, at least one of the shaft will carry two or more gears. This is in stark contrast to the simple gear train, because in simple gear train all the shafts were carrying one gear. Here you see the intermediate shaft is carrying two gears. Now let us see how it works. As usual, module of all the gears are supposed to be identical. Actually what is required technically is module of gear 1 and gear 2 is supposed to be equal. Similarly, module of gear 3 and gear 4 is supposed to be equal. There is no technical requirement that module of gear 2 be equal to module of gear 3. But this is in just to sort of be universally sort of universal standardization will sort of make life simple both for the designer and as well as for the assembly line people to have modules of all the gears in the gear train to be identical. So the modules of all the gears in this compound gear train are identical, not by any technical requirement, but because in order to avoid confusion even in the assembly line process, that's why they would like to make it as a compound gear train. So what we will do is that we could apply law of gearing for each stage, and we will remember that for external gearing the sign of it is reversed, and for internal gearing the sign of it does not reverse. So in this case what we have is the following. Between 1 and 2 we have this formula, omega 1 R1 is equals to minus omega 2 R2. But 2 and 3 being mounted on the same shaft will have the same velocity. So therefore omega 2 is equals to omega 3, and finally omega 3 R3 is equals to omega 4 R4, right? So but with a flip-in sign because it is an external gearing. So there are three formulas that we have. So what we have achieved in compound gearing is this three set of formula: omega 1 R1 is equals to omega 2 R2, omega 2 is equals to omega 3, this comes with a minus sign, and omega 3 R3 is equals to minus omega 4 R4. So therefore what we have is omega 2 R3 is equals to minus omega 4 R4, and therefore omega 4 by omega 2 is equals to R3 by R4 from this side, and from the other side what we will have is omega 2 by omega 1 will be minus, I forgotten a minus sign here, omega 2 by omega 1 here will be uh, R1 by R2. So combining, what we will have is that if we now multiply these two, we get to see omega 4 by omega 1 is equals to R1 R3 divided by R2 R4, right? So this is the input output ratio that we are looking at. So please see that this is equal to R1 R2 into R3 R4, right? So this is the R1 by R2 is the gear ratio which is attained at the first stage, and R3 by R4 is the gear ratio which is attained at the second stage. So what we are doing is that in a sort of geometrical series fashion, we are attaining the entire gear ratio but in two stages. Let's say we require a gear ratio of 9. We will achieve a gear ratio of 3 between in the first stage between gear 1 and gear 2, and we will achieve a gear ratio of another factor 3 between the gears 3 and 4. So the product of the two gear ratios will be the overall gear ratio, which in my example was 9. Okay, so the analysis of this sort of gears is also pretty simple. It is just that you have to do step by step analysis, and you will have to remember that the two gears which are mounted in a single shaft will have the same angular velocity. Okay, so with that let us go to the next feature, which is called a reverted compound gear train. This is exactly what is happening in most of the manual transmissions in vehicles. So let us study this in some depth. So here what we have is the input shaft which carries a gear which is shown in red, and the input shaft, in the input side of this shaft is connected to the flywheel of the powertrain, I mean flywheel of the engine. And this is the output shaft which is shown in magenta, and this goes and feeds into the wheel. Okay, so what happens here is that we have another shaft here which is called the lay shaft, and this shaft is parallel to the input and output shaft. So you have two gears mounted here, gear which is indicated as gear 2 and gear 3, right? So what happens is, first there is a gearing between gear 1 and gear 2. So you attain a gear ratio between gear 1 and 2, but gear 3 moves at the same angular velocity as gear 2 because both of them are mounted in the same shaft. So therefore the angular velocity of gear 3 is same as gear 2. Angular velocity of gear 2 is given by the gear ratio, or the ratio of size between these two gears, gear 1 and gear 2. Once you find the angular velocity of gear 2, you can find the angular velocity of gear 3 to be the same as that of gear 2. And finally from 3 to 4 you achieve another gear gear reduction, another gear ratio between gear 3 and gear 4, which is again determined by their size. So now what you have is power flow in this fashion. In the compound gear train, power flow was moving in this fashion. Here you have a more compact layout which saves the space inside inside the car, and therefore you have just a different arrangement. Otherwise this reverted gear train is almost identical to the operation of a compound gear train, but this is what will be used in cars. Another crucial fact that you must realize from this geometry is that R1 plus R2 has got to be equals to R3 plus R4, because if you look at it, input and output are basically coaxial. They are at the same level. So therefore from this blue line, if I have to reach the input line, I have to go by R2 and R1 radial distance. And if I have to reach this output line from this same blue line, I have to go cover a distance of R3 plus R4 radial. So that means R1 plus R2 has got to be equals to R3 plus R4. And since the module of the gears are all identical, it's going to be ensured that the number of tooth in 1 plus number of tooth in gear 2 has got to be equal to number of tooth in gear 3 plus number of tooth in gear 4. Again, it is not a technical requirement that the number that the module of gear 2 and gear 3 be identical. The technical requirement is only between 1 and 2 and 3 and 4. You could technically be correct in choosing different modules for 2 and 3. But then that is not done because more as a part of standardization than anything else. So therefore module of all gears are chosen to be identical in a gear train. And once you have that, the geometrical relationship of the radii boils down to the certain relationship even in terms of the tooth, number of tooth in each gear. So as we derived for the case of compound gear train, we will see that same formula will go through, and the overall gear ratio again will be determined by the gear ratio at the first stage multiplied by the gear ratio in the second stage. The gear ratio in the first stage being N2 by N1, the gear ratio in the second stage being N4 by N3. So this is the overall gear ratio. Now the objective is not just to attain the gear ratio, but to achieve it is in minimal size. The size is indicated by this blue box. This blue box is the gear box, and all the gears will be packed inside this blue box. So obviously you want to make this gearbox size minimal, and it so happens you can work out this as a part of let's say an optimization exercise, and it so happens that the gearbox size will be minimal if the gear ratio in both the stages is equal. We know the ratio for one stage is, let's say, G1 and the other stage is G2. If you choose G1 and G2 to be different, then the overall size of the gearbox is going to be bigger, because you are going to need one big gear to accommodate their unequalness in the gear ratios. Rather, it is better to choose the gear ratios in both the stages to be same. And when you do that, you have to basically ensure that each of the stage brings down a gear ratio of square root G, because finally the product of these two individual gear reduction stages will lead to an overall gear ratio of G. We are interested in the overall gear ratio between input and output, but the designer, in order to keep the space, in order to save the space, will use an individual stage gear ratio to be square root G. And when you do that, you can achieve what the number of tooths that you wish to have on the gear 2 and gear 4, for example, in order to bring this about. Please note that square root G more often than not will not be an integer, and therefore these n, the n which is the number of tooth, will also not, I mean, since these n's are supposed to be integers for sure, this will not be exactly attained, but it will be only approximately attained. I'll show that with an example calculation here. So the question is to design a gearbox to transmit a gear ratio of 7, let's say. So our policy that we need to have a gearbox with minimal size demands that the individual gear reduction ratio should be square root 7. So for this two-stage reduction, first stage should have a gear ratio of square root 7. The second stage should also have a gear ratio of square root 7, and square root 7 works out to be about 2.65. So we want the smallest possible gearbox which can achieve this job, because we are limited by the space constraint. So we choose the smallest gear in this mechanism here, which is N1, to be of 18 tooth, right? 18 is the minimum, because if you go below 18, the gear will have a problem of undercutting with the rack cutter. So therefore 18 is the bare minimum which I could choose. So I have chosen an 18 number of teeth, which is consistent with my calculations of interference and undercutting. So 18 number of tooth on the first gear gives me 2.65 times 18 number of gear tooth on the second gear, which is 47.62. But you cannot have 47.62 number of gears in any 47.62 number of tooth in any gear. So therefore, we choose this N2 to be 48 rather than 47.62, right? Similarly, what we know as we have derived N3 plus N4 is N1 plus N2. So therefore, N3 plus N4 with N4 is 2.65 times N3. So therefore, N3 plus N4 is 3.65 times N3, and that has got to be N2 plus N1. With our choice of N2 as 48 and N1 as 18, this comes out to be 66. So therefore, N3 comes out to be as 18.1. Again, we cannot have an 18.1 tooth in a gear blank. Rather, we will have this to be 18. So we will make a choice of N3 to be 18, and that leads us to N4, which is 2.65 times 18. That works out to be 47.6. Again, this is not feasible to have 47.6 tooth in a gear. So rather, we will choose this to be 48. So N4, or the number of tooth in gear 4, would be 48. And as a result, the actual gear ratio will be 48 by 18 whole square. So there is 18, 48, 18, 48 in both these stages. So actual ratio will be 48 by 18 whole square, which will be 7.11. So that's what, I mean, this is to exemplify what I said. If you are looking for gear ratio of 7, you will not be able to attain that exactly. You will be able to hit a close value, which is 7.11 instead of 7. This condition has arises simply from practical considerations that obviously you cannot have a gear with a fractional number of tooth. You have to have gear with integer number of tooth. So because of that, and because of the criteria that you want a gearbox with minimal size, you have this slight discrepancy, which is what you will have to work with. And this cannot get mitigated using any other academic formulas or anything like that. This is just a working formula which is used because of practical considerations, and you will do well adopt this situation. Now like to show you an animation of exactly how a automobile transmission works. So there is a beautiful animation which I found in YouTube, and I'm now going to play this for you. This will exactly elaborate how our manual transmission system in a vehicle works. This is not about automatic transmission system. This is manual transmission system, and you should be able to understand exactly with this background how our manual transmission system in vehicles are working. So I will let the YouTube video play it out here for a while. It is a 5-minute video, so I'll let that run. And once this YouTube video plays out, if you have any questions associated with the lecture topic or any other related questions based on this video or anything, we can have an interaction on that. So please look at this video. So this is the engine. This is something that we have not talked about in this talk, but I'm sure you are aware that this is a reciprocating engine. Basically, it's a slider crank mechanism in the context of mechanisms. And this is the power hub. This is what produces the power. So this is where the power is born, so as to say. The thermal energy is converted to mechanical energy, and this is where the engine ends with the flywheel, right? And from the flywheel, he will show the clutch plate also. So this is the clutch plate. So clutch is like a mechanical switch. When the clutch engages or disengages, the power is transmitted or it is stopped. So this is the operation of a clutch. Clutch can operate in using the principles of hydraulics. So the clutch pedal basically is engaging or disengaging with the flywheel. When it is disengaged, as you see in this condition, no power is getting transmitted. And when the pedal is released, then the plate is engaged, and now you get to see that the power is getting transmitted. So all of these gears are rotating when the clutch pedal is released or the clutch plate is engaged. So from the clutch we have the gearbox. This is basically where the transmission starts. So this is the input shaft of the gearbox, and here we see that the blue gear is in mesh with the red gear. So this is the input the red shaft that you see is the lay shaft. Okay, this is the gearbox, this is the input, and this is the lay shaft, and the output shaft is this golden shaft, which is shown in this color. This is the output which comes out from the transmission. So in this condition, if you observe carefully, the shaft is not rotating. It is only that the gears are rotating, because the shafts are actually rotating, moving freely on each of these. The gears are rotating. I'm sorry, the gears are rotating freely on the shaft. There is no engagement between the gear and the shaft. The engagement is brought about through this dog clutch. So when the dog clutch engages to any one gear, then the rotational motion of the gear will be conveyed back to the shaft. So we'll see all these in the animation. And here is a gear selector mechanism. So the gear selector rod that you see in the car basically engages the dog clutch to different gears. So when first gear will happen, this dog clutch will engage. Please see that in first gear, you will be able to see that in a while. In first gear, you have the output shaft connected to the largest possible gear, which means you attain a high speed reduction but a very high torque amplification also. And here it is shown that when the dog clutch is engaged, the output shaft is rotating. It's rotating at the least speed, but it's carrying the maximum torque. In second gear, if you have to go, firstly when you bring it to neutral, you disengage this gear and then you engage it in the second position. So this gear selector mechanism will just go from one side to the other, passing through the neutral, and then you will have it in third gear. What is not shown here is that you should do this operation by releasing the clutch or by disengaging the clutch plate, I will say, because if you operate this with the clutch plate engaged, then the input power is still there. You should not try to do that, because then the system can fail, right? Because it will break. The input power is sort of switched off because the clutch plate is disengaged, and then you should try to move around these gears. And the last gear that you see here on this yellow is basically the reversing. As you see in most of the other gears, there is only a red and blue pair which is coming in engagement. Only in this last gear pair you see a yellow gear. So this is the idler gear. So here you will observe that the motion of this blue gear is opposite. So if you wish to reverse it, it will be in this engagement, and the output shaft will now rotate in the opposite direction. So this is how the manual transmission system in our regular car was. This is the differential part. So these are bevel gears for you, and this is actually an example of a planetary bevel gear system, the differential. So we will not be able to talk about planetary bevel gear system or differential system, but basically the reason why differentials are used is because you need two outputs from the same input. So that's what this animation shows. So this animation, as I said, it is from YouTube. This is a nice and interesting channel. There are lots of interesting animation about practical mechanisms. I strongly encourage you to visit this site and keep looking at it. I see a few questions lined up here. So VC Wasavi is asking, what is the meaning of contact ratio 1.3 or 1.4? As I said, contact ratio cannot be 1 or 2. Contact ratio is very rarely it is possible to have a contact ratio of 1 perfectly, which means always one pair of teeth is in contact. Similarly, a contact ratio of 2 would mean always 2 pair of teeth is in contact. In similar terms, if you have a contact ratio of 1.5, it essentially means for half of the time 1 pair of teeth is in contact, and for half of the time 1.4 pair of 2 pair of teeth is in contact. So for half of the time, if 1 pair of teeth is in contact, for other half of the time 2 pairs of teeth are in contact, then we will say the contact ratio is 1.5. Similarly, you can understand 1.3 or 1.4 similarly means that in a greater half of the time it is 1 pair of teeth that is in contact, and in smaller half of the time it is 2 pair of teeth that is in contact. So that is what is meant by contact ratio 1.3 or 1.4. So 1.3, 1.4 is just a guideline in order to make it, it's a guideline for us to make sure that the contact is always there. If it is below 1, for example, then the contact will be lost. If you, for example, choose a guideline to be contact ratio of just 1.1, then there may be certain eventualities where it will fall below 1, and in which case it is very detrimental to the operation of the transmission. So 1.3, 1.4 is a number which has been arrived at through suitable empirical and experiential knowledge. Okay, we'll move to the next question. What should be the maximum center distance allowed between the first driver gear and the last driven gear in a gear train in order to minimize energy losses? See, the question of energy loss calculations will come in only if we are able to do a detailed analysis involving the friction of the bearings, friction and the other parasitic losses. It is not going to be dependent upon the maximum center distance directly. The amount of losses that you can imagine that if you have to move a heavier gear, you have to, the starting torque that is required is going to be huge, because from its standstill condition it has to start rotating, which means it has to pick up a certain velocity, and after that possibly you don't require that much torque. So all this energy is going to be an overhead to the engine. It was not supposed to make this initial motion, but it is making, it is setting that initial motion, it is triggering that initial motion, and as a result that's a energy loss overhead. So technically speaking, for the purpose of this course, there is nothing like a criteria that we can say that this is the maximum center distance allowed between the first and the last gear, and only then the energy loss will be minimum. There is only a guideline that we are recommending, that don't unnecessarily prolong the gear train over large number of gears over large distances, because in so doing you will have a large energy loss. If you don't care about the energy loss, for example, in certain applications you may think that anyway the energy requirements are minimal, I don't mind doing it with a gear, then you can as well do it in a gear. There is nothing that, no technical requirement which says that you cannot do it with larger number of gears. You can do it, but it is only that you will incur the energy losses. If you think energy comes to you only at a premium, then you should not use that. That's not a good design. That's all I will leave you with. Okay, VC is asking, if module is not the same in given pair of gears, then how will it affect the contact? Please look back at the first lecture. I have explained this part in detail. The lectures by now I'm sure are videos are available in the course pack. The answer to this question is, why is module of two engaging gears going to be same, has been worked out in detail right on the first day of the lecture. I'll advise you to go through that part. For higher velocity ratio, which type of gears are used? SUCET is asking. I think these topics we have covered in the first day of the lecture, but none the same, since you have asked for a higher velocity ratio, maybe one gear arrangement is the best, but here we are talking only about spur gears, and we understand spur gear, though it is the simplest possible gear, it has very many applications, and you have seen as of now that the ready application of it was in the context of automobile transmission. Some automobile transmission obviously will have helical gears, because helical gears, as I said, have smoother operation. But in this course we are talking about spur gears alone. There are other type of gears which can give a higher velocity ratio if you want it. There are other type of gears which can work with different other types of shafts. Spur gears works on the principle that it transmits motion between two parallel shafts. There are other gears which we talked about which can work with other types of shaft. So please look at the first lecture again if you wish to. Okay. Okay, again we have a similar question as we used to have. So GGIPG is saying that if you have a minimum number of teeth requirement of 18, that is not there in cycloidal, so therefore cycloidal is better, is the argument. Cycloidal is better in terms of undercutting, but undercutting interference is not the only aspect of this game. There are other aspects of this game, and as I said, for example, if you have assembly related problems, cycloidal gears will give you a very bad performance. Similarly, the vibration aspects of the gear is going to be very bad with cycloidal gears. So interference, undercutting may, it is obvious that cycloidal gears probably has an advantage in comparison to involute. But from the other aspects, manufacturability aspects, assembly aspects, dynamic aspects, it is involute gears which are better off, and therefore we use involute gears rather than the cycloidal gears predominantly. But yes, to get away with the problem of interference undercutting, therefore we suggest this very simple rule that always work with involute gears with less than with the number of teeth greater than 18. If you have number of teeth to be greater than 18 for a 20-degree pressure angle gear, then you can be sure that there is no interference. So that's how we solve our situation. Yeah, TPC is asking about whether the dog clutch is mounted on the shaft. Yes, dog clutch on one side is connecting the shaft, and on the other side it is connecting to the gear with which it is engaging. BMSC is asking why is there only one reverse gear. Usually in reversing we don't think of moving at very high speeds. The only requirement is it should be able to deliver high torques, because if we are reversing, let's say, in a slightly uphill region, or if the vehicle is fully loaded and yet it has to reverse. So the torque requirements are there, the speed requirements are not there. The speed can be dead slow while reversing. So therefore while reversing we don't have such a diverse requirements, at least in terms of speed. We have only requirements in terms of torque. So therefore there is no point in having a large number of different reverse gears. A single reverse gear will do it. A single reverse gear which supplies low speed but a high torque is enough for our application. Because while reversing, as per road safety rules, you should not reverse at very high speed. If you are doing that, you are doing it at your own risk. Okay. Does IGC PGB is asking, does gear geometry depend on speed? No, gear geometry does not depend on speed. Gear geometry depends only on the requirements of fundamental law of gearing, and as we talked over these last 2 days, it is the involute gearing which definitely satisfies fundamental law of gearing, and that is what has an advantage, and using that advantage or exploiting that advantage, as of now most of the gears are involute. Yeah, TPC is asking about whether the dog clutch is mounted on the shaft. Yes, dog clutch on one side is connecting the shaft, and on the other side it is connecting to the gear with which it is engaging. BMSC is asking why is there only one reverse gear. Usually in reversing we don't think of moving at very high speeds. The only requirement is it should be able to deliver high torques, because if we are reversing, let's say, in a slightly uphill region, or if the vehicle is fully loaded and yet it has to reverse. So the torque requirements are there, the speed requirements are not there. The speed can be dead slow while reversing. So therefore while reversing we don't have such a diverse requirements, at least in terms of speed. We have only requirements in terms of torque. So therefore there is no point in having a large number of different reverse gears. A single reverse gear will do it. A single reverse gear which supplies low speed but a high torque is enough for our application. Because while reversing, as per road safety rules, you should not reverse at very high speed. If you are doing that, you are doing it at your own risk. Okay. Does IGC PGB is asking, does gear geometry depend on speed? No, gear geometry does not depend on speed. Gear geometry depends only on the requirements of fundamental law of gearing, and as we talked over these last 2 days, it is the involute gearing which definitely satisfies fundamental law of gearing, and that is what has an advantage, and using that advantage or exploiting that advantage, as of now most of the gears are involute. Okay, BMSC is asking about double clutch mechanism. This talk is not about clutches, this talk is about gears, so I would like to keep it that way. If you like to know about clutches, please read any design of machine element book that will have it. But this course is about kinematics and dynamics of machinery. This is about mechanisms. Gears is that we are talking about as a part of mechanisms. The last part of this talk, which is going to be on planetary gear trains. So let's cover that up right now. So as the name suggests, planetary gear trains are gear trains wherein we will have a sun gear, a planet gear, and an arm or a carrier. So till now what we have been looking is just in the condition where the arm is fixed. So we have been looking at a fixed basically gears mounted on two shafts which does not have any translational motion. It has only rotational motion. It rotates about this axis. Now we will look at the situation where let's say the sun gear is having a fixed shaft. I mean the sun gear will rotate on a fixed shaft, but the planet gear will be mounted on an arm gear, on an arm or a carrier, and the arm itself will rotate. So as a result, the planet will roll without slipping on top of this sun. So that's something similar to the motion that we observe in the planetary systems. The Earth rotates as well as revolves around the sun. Similarly, this planetary gear will rotate about its axis because it has a certain motion, and because it is being carried over an arm and the arm is undergoing rotational motion about this point, you will have a revolutionary motion also. So the planet will rotate about its axis and the arm will cause the revolution of the planet about the entire periphery of this sun gear. So you will have a very nice condition which is mimicking the motion of planets. That's why it's called planetary gear train. It is also called an epicyclic gear train because, as I just said, this is identical to the motion of the planet circle rolling without slipping over the sun circle. So if you hold the sun circle fixed and if you let the planet circle roll without slip on the periphery of the sun, then as you know from elementary geometry, every point on this planet will or rather a point on the periphery of this planet will generate a curve which is called an epicycloid. So accordingly, this gear train is called an epicyclic gear train. So using the concept of relative motion, we can understand that there are two types of motion that is possible in this planet. One is that the motion if the arm were fixed. If this arm is supposedly fixed, then this gear train is no different from a simple gear train. A simple gear train is just that there are two gears and they are in engagement and there is a transmission of motion. So that part is what we have already studied in simple gear train, and in fact this is not even a gear train because there is just two gears, right? So that part is easy. So what has now, the complexity which has arisen now is this, that the total motion of this planet gear is brought about due to the motion due to the fixed arm plus motion of the arm. So the rotational effect of this planet was always there even if the arm were fixed. The revolution effect has now set in because the arm is set into rotation about the same axis as where the sun is rotating. So therefore you have a combination of rotational motion as well as revolutionary motion of the planet, and this is what we need to analyze. As I said, motion due to the fixed arm is equivalent to the analysis of a simple gear train. What we will do here is that we will adopt a convention that clockwise rotation is positive. Before going further, I must warn you that there are different ways of analysis of planetary gear trains. There are different books which suggest different ways and means for analysis of planetary gear train. I have adopted a pretty simplistic approach, what I believe is a pretty simplistic approach of the analysis of planetary gear train. I mean, the reason I am talking about this is because you will see different books will have different conventions and different ways of analysis. Possibly all of these analysis methodologies are correct. I am not arguing about that. I am simply giving you my good word of advice that instead of trying to learn different methodologies right at this early stage, the risk involved in trying to learn from different books proposing different methodologies is that you might as well get confused, and you might also be prone to error in the sense that you will adopt some part of a certain methodology and some part of some other methodology, right? So if you mix and match these methodologies, it can be very dangerous. So therefore my strong advice to my students in my class as well as you guys would be to learn the methodology in one consistent fashion, right? Please practice problems across the different books, but do the problems across the different books in one methodology. Be confident that you have learned the methodology. After that, if you wish to learn the other methodologies, you are most welcome to do it, and in fact you will be able to gain further knowledge, but you will not get confused. If you right in the first day, if you try to look at all the different methodologies, it will be more confusing rather than illuminating. So accordingly, I will present this analysis topic in one and one clean way, hopefully, so that your this methodology is clear to you, and I will advise you and suggest you to adopt this methodology in the solution of the problems that have been already posted in the assignments, as also you can practice problems from other books if you want. If you feel that this methodology is convincing and it is comfortable to you, please you adopt this methodology, and later if you wish to gain further knowledge, you can supplement this knowledge with other methodologies given in other books. But I will really warn you not to mix and match different methodologies, because I know in some other books the convention would be counterclockwise will be taken as positive. And not only that, there are many different methods across the different books that are there in the market. So don't confuse yourself by looking around different books. Adopt a single book which presents the matter in a clear, concise and consistent fashion, and simply practice different problems using that methodology. Okay, now we go ahead with the methodology. So the analysis proceeds in the following condition. We understand that the total motion can be decomposed into two parts, one in which the motion of the arm is fixed and the other in which the arm is moving. And in fact, the total motion of this gear train is going to be the superposition of these two motions, because one in which the arm is fixed is as good as a simple gear system, and the other in which everything is getting fixed to the arm is, in relative velocity terminology, it can be very easily understood in the following fashion. If you think about an observer who is actually sitting on this arm, to him, if he makes experimental measurements of different velocities, it will appear that this gear train system is just a simple gear train system, because sitting on the arm, the observer will be unable to identify that the arm is moving. He will be able to identify only the planet and the sun is moving. He won't be able to identify that the arm itself is moving, right? So therefore, first we try to analyze this motion which is with respect to the arm, right? But then that is not the real motion that as we will see from an inertial frame. The motion that we will see from the inertial frame is the motion that is as observed by an observer fixed to the arm plus the motion of the arm itself, because that's the concept of relative velocity. Relative velocity says motion with respect to a moving frame plus the motion of the moving frame itself is the motion of as observed from a inertial frame. So therefore, if we want to understand what is happening with respect to the stationary observer, then we will first try to decipher what happens with respect to an observer fixed to the arm, and then simply add the motion of the arm itself. If you do that, then you are going to ascertain what is the motion of any component in this gear train. So that is exactly what we will do, and we will do it in a tabular fashion. So we will analyze the following two conditions. Once we will take the arm to be fixed. If the arm is fixed, the analysis is as simple as a simple gear train. So in this case, if the arm is fixed, it is a simple gear train between the sun and the planet. The sun rotates in this fashion, which is clockwise, and the planet rotates in this fashion, which is also clockwise as per the diagram, but it should be the other way around because it is a simple gear train if the arm is fixed. So none the same, I guess this drawing was done to show that both of them can have clockwise motion if the arm has a certain anti-clock, if the arm is having a certain motion. But none the same, at this stage what we are interested in is to analyze the condition that what happens when the arm is fixed. when the arm is fixed and the sun is having a velocity which is given by omega s, then the planet will have a velocity which is minus rs by rp into omega s. This is exactly the simple gear train formula, and the minus sign here will be taking care of the directions of rotation. These arrows are just indicated symbolically. I mean, if you what will happen is that if the numerical value of the angular velocity turns out to be negative, it simply means that the direction of the arrow that has been marked here in this diagram needs to be reversed, right? So that we can incorporate quite easily. So this is the first condition which is shown in the first row, which is said to be the condition wherein the arm is fixed. The next condition is even easier, which is everything else is fixed to the arm. Remember, the total motion is the superposition of the motion that has been obtained in the situation that arm is fixed plus the motion of the arm itself, which essentially means that on top of this motion we have to superpose the motion of the arm, which is denoted by omega a. So this line is even easier to analyze, that we simply say everything in this mechanism is getting tied up to the arm, and whatever is the motion of the arm, everything else will have the same motion. The idea simply meaning that you superpose the motion of the arm with the motion of the components of the mechanism with respect to the arm, right? And therefore the total motion is going to be the sum of each of these two entries in a particular column. So the motion of the arm, therefore the total motion is omega a, the total motion of the sun is omega a plus omega s, the total motion of the planet is omega a plus omega s into minus rs by rp. So what we have are therefore three variables, omega a, omega s and omega p. So what we need to for the solution is that if any two of them are known, then we can determine the third. There are three components, remember, the arm, the sun and the planet. But the total motion of each of these three components is determined by only two variables, omega a and omega s. So if we know the arm speed and the sun speed, then we can determine the planet speed. So in other words, we require two inputs to determine the output coming out from the planet gear. This is sort of different in planetary gear system as opposed to a simple gear system. A simple gear system or a compound gear system is a single degree of freedom mechanism, that is one input, one output. Here we require two inputs to generate a unique output. Alternatively, we could extract two outputs from a single input. So in that fashion, it's a 2 degree of freedom system. So after we obtain this final row, what we decide is the following, that if, for example, the sun and the planet motion is given, we can recover the arm motion by solving two sets of linear equation. Omega a plus omega s will be given, and omega a plus omega s into minus rs by rp will be given. From these two linear equation, you can definitely recover what is omega a and omega s. But understand that omega a is the arm motion, omega s is not the motion of the sun as observed from the inertial frame. The motion of the sun as observed from the inertial frame is going to be omega s plus omega a, right? Similarly, planet motion is going to be this formula after you determine what is this variable omega a and omega s. So the point therefore is, given two of these variables, any two of these variable, omega s, omega a or omega p. Omega p is this quantity, omega a minus rs rp into omega s is this quantity. So any of these quantities, if it is given, you will be able to determine the other quantity. So capital omega s by omega p, that means this by that, sun by planet. The total motion of the sun is capital omega s, the total motion of the planet is capital omega p. So the final gear ratio between the sun and the planet, if that is what you are interested in, is this. So now you can realize what is the advantage of using a planetary gear system. If I can independently control the arm speed using a planetary gear train, I can attain any gear ratio that I want, because I have the gear ratio dependent on omega a. So omega A is a new control parameter which is entering my gear ratio. If I can independently vary my omega A, I can get any ratio between the sun input and the planet output, or planet input and the sun output. Either way it can work. So therefore this is one advantage which is actually exploited in automatic transmission system where independently if you can give another feed, you can get any transmission that you want. Any gear ratio that you want can be obtained by omega A. By any I simply mean that a reasonably large gear ratio that is possible. Whereas if I stick by my simple gear train analysis or compound gear train analysis, there is only a fixed ratio which I can obtain by using a fixed gear, by using two fixed gears. If I have a certain diameter, certain size of these two gears, sun and planet, using a simple gear train arrangement, I will be able to get only one ratio, nothing else. But if I have a planetary gear arrangement, and by independently varying the speed of the arm, I can now get any gear ratio as per this formula, because omega A can be independently varied. Again I say, I can, by varying this omega A, I can get different gear ratios as per my wish, and that is very well exploited in the automatic transmission system. What we have seen in the YouTube video was the manual transmission system, and what we are now talking about is the automatic transmission system. But I must say there are many flavors of automatic transmission system, continuous variable transmission being one of them, and there are other flavors also. We will not get into too much details about the nitty-gritties of automatic transmission system, but none the same you must realize that epicyclic gear trains are used in automatic transmission system. So this is the point, that the gear ratio can be controlled independently by independently controlling the arm speed. This was not possible in a simple gear train or a compound gear train. Once you fix the size and the number of teeth of these two gears, then everything is frozen and it cannot be varied. But now if you can take, let's say, the output from the battery and independently vary the arm speed, using the same arrangement you can get different gear ratio, right? So that's very nice thing about planetary gear ratio. So as I put it here in this last bullet, that a large range of gear ratio can be obtained, and the best thing about this gears is that it is actually taking much less space. It can be obtained in a very small uh, space. It can be obtained under a very restrictive packaging constraint. It can be obtained in very small sizes, and this is a very important consideration when it comes to different automotive applications. As I said, it is used in automatic transmission. Another very nice application of this planetary gear train is in the fact that, as you realize, that it's a 2 degree of freedom system. So at times you will require to achieve two outputs from a single input, and this can be achieved from a planetary gear train. In fact, that is what happens in the differential of the car. The car, when it is taking a turn, the two wheels, the left hand side and the right hand side wheel, needs to rotate at different speed, because let's say if the car is rotating leftwards, then the left wheel needs to rotate at a different speed as compared to the right wheel, because the right wheel will be executing a longer curve and the left wheel will be executing a smaller curve. So accordingly, the two speeds will have to be adjusted, and such that the car moves synchronously in on both the sides. So this is achieved using differential. Let me just elaborate to you what I meant here in the notes. So let us say the car has to execute a turn leftwards, as I said. So obviously the distance traveled by the left wheel. So this is the left wheel path and this is the right wheel path. The distance traveled by the left wheel, I will call this something like SL, is less than SR, right? So therefore, if both the wheels have got to complete the motion at the same time, let's say I was traveling from a straight path and then I have to take a bend which is in the left direction, right? So accordingly, from this instant to this instant, if the left wheel has traveled SL, the right wheel will travel from this instant to that instant a greater distance. which means the right wheel must rotate faster such that in the same time it can complete that greater distance, right? So therefore, as opposed to the motion on a straight line where we understand the left and the right wheel will have to move identically, when the car is taking a turn, the left wheel and the right wheel have to execute motion at different speeds. If you are taking a left turn, then the right wheel has to move faster. Accordingly, if you are taking a right turn, the left wheel has to move faster simply because it has to compensate for the extra distance that it needs to travel. So now the ultimate powerhouse is the engine. There is only a single powerhouse, which is the engine. There is a single output shaft which comes from the engine. But from this single output shaft, you have to generate single engine output shaft. You have to generate two different feeds, which goes into the two different wheels, right? The way to attain it would be using a planetary gear. So in fact, the exact mechanism by which this is attained is the differential, which is what you have seen even in the YouTube animation. So what happens is that the power first goes to a differential, and through the differential it goes to the left wheel and the right wheel, either for a front wheel drive or for a rear wheel drive. It has to pass through a differential, and the differential essentially enables the two outputs to be at different speed. And this is all possible because it's a 2 degree of freedom system. So the differential of a car happens to be a planetary gear mechanism. The only difference between the planetary gear mechanisms that we are studying presently and the differential is that differential is comprising of a planetary bevel gear mechanism. In this talk we are studying planetary spur gear mechanisms. But as I said, it is a very small incremental change from at least from kinematic perspective. If you can understand the spur gear, you will also be able to adapt to the bevel gear situation, and with a little bit of effort you should be able to understand that the differential of a car or any automobile for that matter is essentially a planetary bevel gear mechanism. Another example I can give you is about the clocks. In the clocks, let's say you will require two outputs, one output for the hour hand and the other output for the long hand. And obviously these two are moving at different speeds. So from the same primary battery fed motor, if you have to extract two outputs, you have to need a 2 degree of freedom mechanisms, and in clock mechanisms you do have applications of planetary gears which extracts these two different outputs from the single input. All that is possible because planetary gear mechanism is a 2 degree of freedom mechanism. Okay, I'll have one more example of planetary gear train analysis to talk about here. So here what I have done is that on top of the sun, planet and the arm, I have put a ring gear also, which is like having an internal gearing with the planet gear. So the planet gear and the ring gear are in an internal gearing arrangement. So what we see here is a sort of a schematic diagram. This is called the Levi schematic diagram, because usually we would not like to draw these elaborate diagrams. Rather, what is preferred is a schematic diagram of this sort. This can be easily understood. This is a sort of side view, but it is not the side view as you would learn in an engineering diagram, because in an engineering drawing sense, because this is a schematic diagram. What is done here is to show the engagement. We have just left a gap between the two lines, and here taking the benefit of computer drawing, I have been able to show this in exactly the same colors as has been shown in the front view. So for example, the sun was shown in red. I have showing the side view of the sun in this thin red line. Obviously this is not an engineering drawing course wherein we mark the thickness in its exact proportions, but the information that we need is only about the connections, right? So here we see that there is a sun gear, there is also a planet gear, and if you carefully see this green line, it shows that the planet gear is mounted on the carrier or the arm, right? This green portion is the arm. In front view it was the arm, so I have kept it that way even in the side view, and this is sort of denoting that within a bearing on the arm, the planet gear is mounted, and the planet gear is also meshing with this magenta object, which is the ring gear. So this is indicating that there is a internal gearing arrangement between the planet and the magenta. So again, from geometrical considerations, we have the radius of the sun to be the radius of the ring gear, I'm sorry, this is the radius of the ring gear. The radius of the ring gear is equal to the radius of the sun gear plus the diameter of the planet gear. Radius of the sun plus diameter of the planet is equals to the radius of the ring gear, right? And again, if we adopt the approach that all gears within a gear train has got to be made with the single module, then it boils down to the fact that the teeth, the relation radius, which is a geometrical relation, will translate to the same relation in terms of teeth. So number of teeth on the sun gear plus 2 times number of teeth on the planet gear has to be equal to number of teeth on the ring gear. Again, we adopt a tabular approach, and in this table, as usual, we will try to analyze two different conditions. One in which arm is fixed. When the arm is fixed, it is like a simple gear train wherein the motion from the sun can be conveyed to the motion from the planet. So if omega s is assumed to be the motion of the sun as observed from the arm fixed condition or from the observer who is sitting on the arm, then if omega s is taken to be that, omega planet can be referred to as minus rs by rp into omega s. And finally, if this is the planet gear speed, then the ring gear speed can be determined as rs by rp into omega s into rp by rr. rr is the ring gear radius. And then the next condition, that when everything and when all the components are fixed to the arm, then each of these components are having a speed omega I. This essentially means that we are superposing the motion of the arm onto each and every component. The first condition, when with arm being fixed, is equivalent to saying that we are analyzing the motion with respect to an observer who is fixed on the arm, right? The second condition is saying that on top of this motion, which is attained in the first row, we are going to superpose the motion which is equivalent to the motion of the arm, and the superposition is the final row of this chart, and that superposition is saying that the total motion of the arm is omega a, the total motion of the sun is omega s plus omega a, and the total motion of planet is likewise given by this, and the total motion of ring is likewise given by that. Remember, though the components in this gear train are 4, namely arm, sun and planet, there are only 2 variables that matter. So given any 2 of these motions, if you know what is the arm motion in totality, omega a is known. If you know what is the sun motion as measured by a stationary observer, then you know what is omega a plus omega s. Then using these 2 quantities, you can determine, let's say, omega s. And once omega a and omega s is known, planet motion and ring motion can be recovered, right? Similarly, if any 2 motions is known, then the other 2 can be recovered. If the planet motion is known, then this quantity is equated to that motion. If the ring motion is known, then this quantity is equated to that motion. And as a result, at the end of the day, you will have 2 linear equations to solve for omega s and omega a. Once omega s and omega is determined, the motion of any component in this mechanism can be very well determined. So this is how a planetary gear train mechanisms can be analyzed. Please don't get perplexed by as I said, there are many other ways of solution. I'm not saying they are wrong, or I'm not saying that they are more difficult. I'm just saying that please don't get perplexed by looking at different methods and trying to mix and match these solution techniques. That may actually be a very risky proposition. Please, in your learning stages, adopt one method, understand that method very confidently, very correctly, grow in comfort level, and then if at all, if you want to explore other options, you are free to do so. So with this, I have touched upon the topics which were told in the syllabus on this. as I said, I have mostly taken this lecture material from Ghosh and Mallik's book. Also, Norton's book and Shigley's book are universally accepted books. You could read and solve the problems in these books. And as I said, not only Ujjwal Rane's site, there are many other nice animation sites that are available in YouTube and other related stuff, like this one that I gave here. There's actually an entire website, how stuff works. So in this website, how stuff works, you will find animations of different kinds of machines. Not only mechanical transmission, hydraulic transmission are also shown. So these are very nice and interesting visualizing aids to enable you to understand the motion, and visualization of motion I think is very important in your learning process of mechanisms. So with this I will close my talk here, but there is adequate time left for any interaction. So if you wish to have any interaction, I will warmly welcome any interaction that you wish to have. I hope this last part of planetary gear trains is clear to you. I understand, as I said, that the method that I have proposed here is probably not in alignment with the different textbooks that are available in the market, but I find it pretty easy to both understand and teach. So this is something that I am proposing, and really there is no point in trying to confuse you with too many different methods at this stage. Okay, why using idler gear for reversing? KSRCT is asking, why do we use idler gear for reversing? If we use only two gears, then the direction in a simple gear train, as I talked, I think I showed it here. In a simple gear train, or maybe I can work it out once more if you want. In a simple gear train of this kind, the direction of motion of the input and the direction of motion of the output is reversed. If this is going to be in the clockwise direction, the other one is going to be in the counterclockwise direction. Now what you have seen from the schematic diagram of the transmission system here is that all of these blue gears till this point is going to transmit motion in only one direction, motion and torque both in only one direction, which is fine for the forward drive. But now if you want to reverse the gear, it is not possible to do it with one gear pair. If you just put an idler gear pair, if you put an idler gear in between this piece of red and blue gear, then you will achieve the condition that the blue gear is rotating in the opposite sense. I will show that to you here. So if you have an idler gear in between, the gear ratios will remain unaffected, but the direction will be reversed. So here if you have the input to be clockwise as usual, then the idler gear will rotate anti-clockwise, and if it rotates anti-clockwise, this will rotate clockwise. So what you have achieved is that the output is taken from this shaft. The output will rotate clockwise when the idler gear is there in between the input and output. Whereas if the idler gear is not there, the input and output is having reversed motion. So here this is clockwise, this is counterclockwise. Here the input remains clockwise, but the output now changes direction from counterclockwise, it becomes clockwise. So between these two, you see that there is a change in direction of the output speed and torque, right? So as in the case of driving a car, we do have requirements where the direction of the output speed and torque has to change. We don't just go in the forward direction, we have to go in the backward direction. This is not true for two-wheelers. For two-wheelers we don't have a reverse gear, because if at all we need to back off, we can just push the vehicle in the backward direction manually and do the backing off. But that is not possible for a four-wheeler because it's too heavy for us to do that. So you need an arrangement which will provide the mechanism by which the output can be reversed. And that arrangement is pretty easy to attain. You just have to put an idler gear in between the input and output. And that is exactly what is shown. Okay, JNTU is asking me how does an automatic uh, gear system work. As I said, automatic gear systems, there are very many variants. Some of those variants are actually patented, and not every details of it will be known if it is patented, but the technology is known. CVT is one popular technology. There are other technologies also, and you can look at these YouTube sites. For example, there are certain websites which will talk about how automatic gear system works. Interestingly, you will find lots of applications of planetary gears in automatic transmission system. But talking exactly about the finer details of automatic transmission system is outside the scope of the current topic. JNTU is asking up to what extent the gear train will be used. You can use the gear train for whatever extent. I mean, by extension, I suppose you are meaning what is the range of distance. There's nothing like a hard and fast rule that the gear train can be used for 1 meter or half a meter. But definitely the losses incurred for a gear train which is long is going to be large. So therefore, to keep at the losses minimal, you should not use a gear train which travels over a larger distance. You should not expect, someone will give you a formula that beyond 1 meter you should not use a gear, you should use a hydraulic. It's nothing, it's never like that. The judgment is always left to the designer, to the application person, because in certain cases actually the efficiency may not be important. For example, in toys, let's say toys which are not even battery operated, manually operated toys, for those kind of applications energy is not a matter of consideration. Gears can be easily made by 3D printing processes. Some of the colleges may be very aware of the 3D printing facility. You just draw the gear in like a ProE or a CATIA kind of a software, a geometric modeling software, and instead of giving a print on paper, you can give a 3D printing facility, which basically means that in some sort of plastics these will be made. And using these gears and using the mechanisms judiciously, you can create different toys. That's in fact how toys are made. And for some of these toy applications, you actually don't need to worry so much about efficiency, because toys are after all toys. Babies will play for it for a while and then it will get broken. What is important is that you must be able to make them in a cheap and efficient fashion. So gears will offer an advantage in that in that regards. So that will be that will be a consideration that you have to take. Whereas if you are talking about a power plant, if you are talking about more sort of engineering applications which have to run over larger periods of time, then energy efficiency is a very crucial aspect, and therefore it is not advisable to go for a gear train which is long and which therefore has a loss in efficiency. Okay, JNTU is asking which gears will have more energy, why will big gears have more energy loss? If you have a small gear, to rotate that smaller gear from its state of rest to a state of a constant RPM, you require very less energy. If you have a large gear, it has large mass, and to bring it to a state of motion from its state of rest, you require a large torque and associatedly large power requirements. So the power requirements come from this attribute that a large gear will require a large, try rotating a large disc and try rotating a small disc. You will realize that obviously from its state of rest to a state of motion, you require large power to rotate a large object, whereas you need less power to rotate a small object. Once the rotation is set up, possibly you can say that there is no torque that is required to overcome the loads. But none the same, you require gears such that they will stop and again they will start into motion, especially let's say in automobile application. I mean, each time you switch off the engine and again restart, this is exactly what is happening. So therefore, if you have a very low transmission efficiency associated with larger gears, then it will be a huge loss. It will be a huge burden for the owner of the vehicle to accommodate this poor transmission efficiency. So therefore, that's not a good idea, right? I hope you got that clear. BEC is asking me application of epicyclic gear train. As I said, epicyclic gear trains are used in automobile application. Epicyclic gear trains are used in clockworks. Epicyclic gear train is used in differential of an automobile, because as epicyclic gear trains are 2 degree of freedom system mechanism wherein a single input can be used to extract two outputs, and this is exploited in a differential. So there are very many different applications of uh, epicyclic gear train. I think it's a good time for me to sign off. I hope you enjoyed the lectures. Thank you very much.